Hello students, in our last lecture we solved 4 examples. Now let us start this lecture with example number 2.5. In the given statement it is written that if the size of a nucleus whose range is 10 raised to minus 15 to 10 raised to minus 14 meter is scaled up to the tip of a sharp pin, and in the statement the range of the tip of the pin is given to be 10 raised to minus 5 meter to 10 raised to minus 4 meter. Now students, here considering the minimum value from the given range, we can consider the size of the nucleus to be of the order of 10 raised to minus 15 meter, and that of the pin is 10 raised to minus 5 meter. Here in this example it is assumed that the size of the nucleus is that of the size of the tip of the pin. Means the size of the nucleus is imagined to be larger. Why I am telling larger? Because the actual size of the nucleus is of the order of 10 raised to minus 15, but here we have to consider that is to be of the order of 10 raised to minus 5 meter. So this 10 raised to minus 15 is smaller than 10 raised to minus 5. So if the size of the nucleus is imagined to be increased, then what should be the size of the atom if the actual size of the atom is 10 raised to minus 10? So we need to find the imaginary size of the atom if the size of the nucleus is assumed to be increased to that of the tip of the pin. So students, here without any calculation or mathematical steps we can get the answer. Here the size of the nucleus is increased to how much time? 10 raised to 10 times, because from 10 raised to minus 15 it is considered to be of 10 raised to minus 5. So what is the difference between these two? So we can easily find that the difference is minus 5, that is new value of the size of the nucleus, minus original value which is minus 15. So minus 5 this as it is, and minus into minus plus, here this minus into minus plus 15. So what is the result? Result is 10. So here power of 10 is 10, means it is increased this much times. So even the size of the atom should also increase that much time. So here original size of the atom is given to be 10 raised to minus 10 meter. So it should be increased by again 10 raised to 10 times. This is original value and this is the assumed value of the size of the atom. This much value will be the assumed value, because 10 raised to 10 times should be multiplied. So result of this will be, you can see here minus 10 power and here plus 10 power. So minus 10 and plus 10, the result will be 0. And we know that if the power of 10 becomes 0, then that is equal to 1. Even anything raised to 0 is 1. If I write x raised to 0, then that will be also equal to 1. And so the imaginary size of the atom will be equal to 1 meter, which is quite large. So students, we know that if this is the nucleus and if this is the electron revolving around the nucleus, then we can say that this is the size of an atom. So if this is of the size of the tip of the pin, which will be very small, which is nothing but the nucleus, then this distance will be of 1 meter. So we can imagine that how small the nucleus is compared to an atom. Now let us see some proper method of obtaining this answer. So here I have considered the data of nucleus. This is actual value of nucleus and this is the imaginary value of nucleus, that is the tip of a pin, and that's why I have used this letter P for a pin. Now here I have used the values for the atom. This is actual value A and this is imaginary value, that is denoted by X. Now here this values N, this value P and this value A is given, unknown is X. So by using cross multiplication method or by taking the ratio, you can apply any method. If you will cross multiply this, then you will get X into N, here say X into N is equal to P into A, P into A. Or if you will take the ratio, then N upon P is equal to A upon X, that is shown here. Now we want to find X, so make the subject X either in this or in this. You will find this step. If I want to make the subject X here, then I'll bring this N here on right hand side, so it will become PA upon N. Or here also we can do the similar type of mathematics. Now after getting this term, we have to simply put the values. Value of P is 10 raised to minus 5. Value of A is 10 raised to minus 10. And that of N is 10 raised to minus 15. Now power of 10 only we can see here. So in the numerator, minus 5 minus 10 will become minus 15, and in denominator also there is minus 15, and so 10 raised to minus 15 in numerator and 10 raised to minus 15 in denominator will cancel out, and so remain is 1. So our answer is x is equal to 1, and definitely we should write a unit. Unit is meter. So 1 meter. Now students, let us imagine the same type of concept in some different manner. Here you can see a hydrogen atom in which nucleus is at its center and an electron is revolving around the nucleus. One more thing, in hydrogen there is only one proton and only one electron revolves around it. So here this is a proton, and that is the nucleus of the hydrogen atom. So now if the size of this nucleus is as shown in the figure, that is of this size, then where would be the electron revolving? So here in this figure you can see the electron is revolving at this distance, but actually if this is the size of the nucleus, then this electron which is revolving around the nucleus will not be at this much small distance. This electron would be at least 1 kilometer away from the nucleus. So just imagine how much power is there in a nucleus, because this electron revolves around this nucleus due to the force acting by this nucleus on this electron. Now let us compare the similar situation for a solar system. Students, here this sun is given at the center, and the other planets, they revolve around the sun. It is similar to that of the atom. Nucleus is at the center, and the electrons, they revolve around the nucleus. So here also, if this is the size of the sun, if this is the size of the sun, then this last planet which is revolving here will not be here. Actually it will be at least 1 kilometer away from this sun which is of this much size. Now next topic is range of lengths. In physics we came across the different sizes, in which the minimum size is of that of nucleus, which is of the order of 10 raised to minus 14 meter, and the large size is of that of the observable universe, which is of the order of 10 raised to 26 meter. So from 10 raised to minus 14 meter, which is very much small, to 10 raised to 26 meter, which is very much large. So for such type of lengths, the special units are used for their measurement. Here some of the special units are given. First is Fermi. 1 Fermi is equal to 10 raised to minus 15 meter. In symbolically, we can write 1 Fermi as 1 F. Second is angstrom. 1 angstrom can be written as symbolically like this: a dot over a capital A, and 1 angstrom is equal to 10 raised to minus 10 meter. Then for very large distances or very large size, astronomical units are used. These two, Fermi and angstrom, were for very short or very small distances or sizes, but here this is for large distances. In symbolically, 1 astronomical unit is written as 1 AU, and this is nothing but the average distance of the sun from the earth, and its value is given here, which is 1.496 into 10 raised to 11 meter. So this is nothing but the average distance of the sun from the earth. Now here in this image you can see an earth revolving around the sun. The actual path of the earth around the sun is shown by green color path, but here this actual path is not exact circular. So considering the average distance of the earth from the sun, the red color circular path is taken, and the distance of earth from the center of the sun is approximately this much kilometer, which is nothing but 1 astronomical unit. Next is 1 light year. In symbolical manner, we can write it as 1 Ly. This 1 light year is equal to 9.46 into 10 raised to 15 meter. Now, this is the distance that light travels in 1 year with the velocity 3 into 10 raised to 8 meter per second. Now here this image represents the distance of a light year. Here a sun is shown, and the radiation from the sun or a sun ray travels the distance and it reaches at this point in 1 year. The speed of light is 3 into 10 raised to 8 meter per second. With this speed, the light travels and reaches at this point in 1 year, and this distance is given here in terms of trillion kilometer. It is 9.5 trillion kilometer. Next unit to measure the large distance is 1 parsec. 1 parsec is equal to 3.8 into 10 raised to 16 meter, and this is nothing but a distance at which the average radius of the Earth's orbit subtends an angle of 1 arc second. Remember, 1 arc second means it is 1 second. Now let us try to understand with the help of this figure. Here the sun is shown by yellow color and this is the earth, and we know that the distance of the earth from the sun is 1 AU, which is nothing but the orbital radius of the earth around the sun. Now if at this point this line of the earth and this line from the sun, if they make an angle of 1 second, then this distance will be equal to 1 parsec. The symbol for parsec is PC, and here this value is given in terms of AU. In our textbook that is given in terms of meter. Now if we draw this type of line here, then this angle will be larger, and as we move away, then the angle will decrease, and finally at some distance this line will make 1 second of an angle, and so this distance is equal to 1 parsec. Now next topic is about measurement of mass. Students, we know that any matter, either solid, liquid or gas, they are made up of atoms or the molecules, and each and every atom or the molecule has mass. Mass is a basic property of any matter. Next thing is, mass does not depend on the temperature, pressure or its location. It means if you take any object and if you measure its mass at one place, and then if you measure the mass of the same object at some other place, then also its mass will remain same. Also, if you increase or decrease the temperature or pressure of that substance or the object, then also its mass will remain same. And we already know about the SI unit of mass. Mass is measured in terms of kilogram. Now students, you don't have to bother about this part, not necessary, because you will not be able to understand about this at present. But one thing I will tell you, that this unit kilogram is considered using some special condition or phenomena or any process. Now in these notes I have written important points. Amount of matter in any substance is called its mass. It is an internal property of matter. Mass does not depend on external factors like temperature, pressure, etc. Mass can be measured with the help of simple balance. It remains same at any place, and the mass playing role in a gravitational force is called gravitational mass. Now students, this unit for mass, that is kilogram, is used for the large objects So we can say that this unit is large unit. But if we want to measure the mass of atoms or the molecules, then this unit is not convenient. And so here also the special unit is used to measure the mass of any atom. The special unit used is atomic mass unit, and its symbol is U. Now what is this atomic mass unit? This atomic mass unit is nothing but it is the 1/12th part. It is 1/12th part of the mass of the atom of C12 isotope. C12 means it is an isotope of a carbon. Once again, what is atomic mass unit? It is the 1/12th mass of an unexcited atom of C12 isotope of carbon. Sometimes atomic mass unit is symbolically written as 1 AMU, or in very short it is simply written as 1U. But this 1U in terms of SI system is 1.66 into 10 raised to minus 27. You can see here the power of 10 is minus 27. That means it is very small mass. So this is for the small masses. To measure the large masses like that of the mass of planets, stars, etc., the normal method cannot be applicable, because if I want to measure the mass of a moon, I cannot take that moon and place it on some machine which can measure the mass. We have to apply some special methods, and such special methods use Newton's law of gravitation to measure the large masses. Now, to measure the very small masses, a mass spectrograph method is used. Means to calculate the mass of any atom or subatomic particles, this type of mass spectrograph is used. Students, in this image you can see the method of mass spectrograph. If you want more information, then you can search in the YouTube. Now about the range of the masses, means very small mass to very large mass. In physics, we come across a very small mass about 10 raised to minus 30 kg, that is the mass of an electron, and a very huge or a very large mass of about 10 raised to 55 kg, which is that of the mass of a known universe. Now about the measurement of time. Now atomic clocks are used for the measurement of standard time. Here an example is given of a use of cesium atom in atomic clocks. This type of clocks, they give us accurate time. This type of atomic clocks are based on the vibrations in an atom. Here in a cesium 133 atom, means this is an isotope of a cesium. In that, in 1 second this much vibrations are carried out, and so due to this it gives an accurate time. These vibrations will not change with time. The clock or a wristwatch which we uses are based on the quartz crystal. Even this is based on the vibration of this crystal, and so even this type of clocks can also give a accurate time. As this type of clocks are having accurate time, they are used for the measurement of standard interval of time. Even in India, this type of clock is placed at the National Physical Laboratory in New Delhi for the maintaining Indian Standard Time. Here, the 4 cesium atomic clocks are placed. Students, read the textbook carefully. Each and every line you have to go through it and underline the important points, because out of this much given statements, few are very important. Rest is only for the information. Now here one interesting thing is given, that we have taken the range of the lengths, range of the masses, range of the time, etc. In all this, one thing came out to be common, that for lengths the ratio is obtained to be 10 raised to 41 for the longest and the shortest distances. Even for the time also, the smallest to the largest is obtained to be 10 raised to 41. Even the range of the ratio of the largest to the smallest masses is obtained to be square of 10 raised to 41. So here this figure 10 raised to 41 is common for length, mass and time, which is something interesting to know. So this is all about today's lecture. I hope you enjoyed this lecture.